small signal stability analysis. And in the first part, we have discussed about the uh, small signal analysis in terms of how we analyze it. And then we move on to discuss the use of model analysis. In the previous slide, if we recall, we had discussed the uh, determination of left eigenvector and right eigenvector. And if we recall from the previous slides, the right eigenvector gives the mode shape, and it is basically the relative activity of a particular state to the mode. And this is what we get it from the right eigenvector matrix here. Similarly, when you move to the left eigenvector, that also gives you the mode composition, saying what is the weighted composition of the original state variable to the mode. So in summary form, the right eigenvector gives the activity of the state variable to the mode. However, the left eigenvector weights the contribution of the given state variable to the ith mode. Now, with this, we had discussed the uh, next about the participation factor. Uh, One thing we must know that this participation factor which we had, it was obtained by the multiplication of the right eigenvector and the left eigenvector. Now, in fact, the left eigenvector or the right eigenvectors individually uh, for identifying the relationship between the states and the modes. Uh, there is a issue for in this case here. So that means it is difficult to use the right eigenvector and the left eigenvector to so as to know the relationship between the states and the modes. Reason behind this is that the elements of the eigenvectors, whether you consider on right eigenvector, so the elements here, this one. So elements of the eigenvectors, they are dependent, they depend upon the units of the states. So if I say this element of the eigenvector matrix, so it will depend upon what is the unit of this state. Similarly, for this case, what is the unit of this state here? And thus the scaling associated with these state variables here. And that limitation or the issue can be resolved uh, by the use of the participation factor, and thus obtaining the participation factor matrix here, which we have discussed last time. So in fact, the participation factor we obtain by the multiplication of the right eigenvector and the left eigenvector, and thus it measures the relative participation of the states to the particular mode, ith mode here. And the multiplication of the two vectors, right and the left, gives you a dimensionless value. And next, we had discussed what will be the steps uh, that we apply to obtain the participation factor matrix. So we have discussed this slide last time. So we move further now, and it was this slide. So here we want to take an example uh, for small signal analysis of a given component, and we take an example from a regulator model. So we have a automatic voltage regulator component, and we want to determine the eigenvalues, the left eigenvectors, right eigenvectors, including participation factor. So this is the complete block diagram representation for AVR. And as you can see here that we have the input state quantity, input variable here, which will be the control signal. And then we have some blocks that presents the elements here in the AVR. And here we have the reference voltage. So this will be from the, you can say, the measurement that will represent the transducer for the measurement of voltage signal from the generator terminal. Then we have the this block, so that is as a first order model for the element, and it is the amplifier. And we also have some limits on the signal here at the output of the amplifier. So we have this voltage signal. Then next element is the exciter, the field circuit of the synchronous machine. So we have represented by first order element here. Then we also have, because the output of the field circuit, that is the voltage signal, we get it feedback through a stabilizing transformer. And this is how we have represented it here, given as a feedback on the input side. So with this block diagram representation for automatic voltage regulator, we want to compute eigenvalues and other model analysis that we want to perform here. So we move next. So with this block diagram, it is possible to have a state space representation, and with the states, what we find here that we can get the states, this terminal voltage states, then we get one state here, we are another state here at the output of the exciter, and one more state at this point here. So altogether we have four state quantities, four state variables, and represented by, let's say, delta x1, x2, x3, and x4. So these are all derivatives here, derivative terms of the state variables of the voltage signal. Uh, and then we can present the complete A matrix here and the state quantities, and then you have the B matrix here at the part, and then control signal. We also have the output variable as in this one. So it will be with, sorry. So with this case, we have the voltage signal at the output of exciter, that is the VF. So it is the VF signal, which is as a output signal here from the block. So with this, we have the unit value in the C matrix as a row vector, and then D element, D matrix is zero here. So we consider some constants values, the values of the parameters here of the system, and we obtain the complete A matrix here. So this is the complete A matrix being represented as this equation here. Right. Move to the next slide. Now we are able to compute the eigenvalues, and thus in the MATLAB software using the EIG function, which is the inbuilt function, so we can get the eigenvalue, and we find here that there are four sets of eigenvalues because the order of the system is fourth, so thus we get four eigenvalues. And we find that the two eigenvalues are complex and they are associated with oscillatory mode. However, the other two eigenvalues, they don't have any imaginary component here, and thus they are as non-oscillatory mode. Now, with respect to the MATLAB code, we have the use of the left argument here for the EIG inbuilt functions here. And thus, we are actually interested to determine the right eigenvector here. And thus, we have the P matrix, which is obtained as this one. So what we find here that along the row vectors, we have the four state variables. And along the column vector, we have the representation of the eigenvalues. So lambda 1 and lambda 2, these are oscillatory modes, and 3 and 4, they are non-oscillatory modes represented as the column vectors here. Now it is possible to have the representation of these quantities in the P matrix as phasor form. So we can have it, let's say, if you consider the quantity here in the polar form, so we get this, and similarly for this case we can guess, and thus with the respect to reference axis we can plot them here, and that gives you the mode shape for the oscillatory mode, because this is the oscillatory mode. So uh, what is the position of these vectors with respect to the reference, that we can get it here, and thus the mode shape. So we will discuss about mode shape more in detail with examples, right? And then we do as reference to these codes, we have the key transpose, that is the inverse of P, and then we complete the right eigenvectors and the left eigenvectors. So with the D matrix that we get here, this one. So D, with the D matrix, what we have actually is the representation of the eigenvalues, because these are the four eigenvalues, and with the D quantity, D variable, we are able to have the diagonal matrix with the eigenvalues positioned along the diagonal elements here. So in the complete D matrix, we have the eigenvalues located diagonally here. Next, we will be interested to compute the left eigenvectors, and this is how we can get it in the matrix form. We had it from the previous MATLAB code, and then we have the right eigenvectors matrix, and as I said that the row wise it will correspond to the state variable, and column wise it will correspond to the eigenvalue. Similarly, for the left eigenvectors, we have the represented here, and now we are able to compute the participation factor, and to achieve that, we will multiply the right and the left eigenvector for each eigenvalue, element by element, to get the complete matrix for the participation factor. So we have represented as P1, P2, P3, and P4. So thus on the rows vector, we have the state variable and on the column vector we have the eigenvalues presented. So with this, so if we want to have the P1, then this uh, right eigenvector, and then this left eigenvector to be multiplied element by element. So we achieve that, and thus we get the complete participation factor matrix. So all this was obtained by the use of these codes here. Now we have the representation of the participation factor. So on the row vector, we have the state variable, and columns wise column vector, we have the eigenvalues representation. Now if you look at the column 1, we find here that for the eigenvalue lambda 1, which is actually the oscillatory mode, that we get it here, lambda 1 and lambda 2. So with this oscillatory mode, we find here that the state variable Vs. So from the column 1, it is suggested that the state variable Vs dominantly participate to the mode of oscillation lambda 1 in terms of the amplitude what we observe here. And thus we can say that this state variable is associated to significant oscillations, and thus it will be the state variable Vs which is more likely to have the oscillation here of the mode lambda 1. Similarly, when we look at column 3 here, in this case we observe that the state variable Vf, it has the maximum amplitude, and in fact there is no imaginary term, but the amplitude is much higher here for the state variable Vf for lambda 3. So here we can say that the state variable Vf, it is more influenced by lambda 3, but this is non-oscillatory mode. Similarly, if you refer to the column, this one, fourth column, then we find here that these three elements, they are 0, and the first element in the column 4, first row, I mean, this has the maximum value corresponding to the lambda 4, and thus from the column 4 we say that is the state variable V terminal voltage, which is more influenced by lambda 4. So thus, depending upon the magnitude of these quantities uh, corresponding to the state variables and the lambda values, eigenvalues, we can know which state variable will participate dominantly to the given mode here. And since we are interested to know the oscillatory mode, so thus we need to know the state variable. So which state variable will participate dominantly to the particular mode of oscillation here. So we move to the next slide. Now we take another example now, and this example is to discuss or to show how the state variables are associated with a particular oscillatory mode. In the previous example, we had just talked about the state variable of a component associated with the mode. Yeah. Now, but we want to take a network example where you find here that it is a three generator machine. It is a multi-machine system where we have generator 1, generator 2, and generator 3. And for each case, we have the representation of the rotor angle here, the state variable. Now, with these generators, which are interconnected in a multi-machine network, uh, uh, in fact, in terms of the stability, when we say uh, it makes no sense saying that the generator 1 it is in synchronism basically, but we have to say that generator 1 it is in synchronism with generator 2 and generator 3, or it is to be said that generator 1 is in synchronism with the rest of the network here. So in other words, we say that the word synchronism it is actually a relative phenomena. So we talk about the synchronism of a one generator with respect to other generators or the network, right? And that's why here we have the rotor angle stability being defined with respect to the relative rotor angle, not just the absolute delta dial delta I. So we say as dial delta ij, which is the difference of dial delta I minus dial delta j here. With this example, we have it from one of the book by Peter and Shaw, I think, and we have the state space matrix A with the given parameters as shown over here. So we have the difference of the rotor angle between the generators. So we are talking about the synchronism of this generator with respect to this and this now. So, and that's why we have it dial delta dot 1 3 and dial delta 2 3 here. Right now, and then we have from the equations of the sync, right? uh, we have the delta variables and we have the omega state variables being represented, and thus we have the A matrix here. Now for this example, the eigenvalues which we have calculated, right? So we have it because we can say one eigenvalue and second eigenvalue, so we have it in this way. Now in these, what we find here that there are two modes here, right? And when we look at the mode 1, it has an oscillation frequency of corresponding to 1.4 hertz, because this is omega. So divided by 6.28 gives you about 1.4 hertz. So this mode 1 is corresponding to 1.4 hertz of oscillation, and this mode 2 it is somewhat higher, right? So now these eigenvalues which we have, it was obtained using the MATLAB aij function here. So next, with these MATLAB codes, uh, we can obtain the D matrix, diagonal matrix, with the eigenvalues placed along the diagonal in the matrix here. So we have them here. Now, this from the previous code as discussed in the previous slides, we can obtain the P matrix, and which is the right eigenvector matrix here. And what we find here that the right eigenvectors, they are placed along the rows. So thus we have the four state variables placed along the rows, and then we have the eigenvalues placed along the column here. So we have lambda 1, lambda 2, lambda 3, and lambda 4. So now with the right eigenvectors, because the right eigenvector gives you about the activity of the state variable. It could be any of the state variable to the ith mode. So if you want to know the activity of this state variable to the mode lambda 1 or lambda 2 or lambda 3 or lambda 4, that way it refers here. Now with respect to the mode 1, what we find here that we have plotted all these quantities, all these elements here, and we find here that the two state variables delta 1 3 and delta 2 3 from here, and then similarly omega 1 3 and omega 3, they are on this side. So what we find here that these two state variables, they are more or less in the same phase. So thus we can say that the angle of oscillation for the generators, they are in the same phase here. Similarly, similar behavior we observe even with the use of state variable angular frequency here. So we say that the two generators, the difference of the angular speed, in fact, they are in the same phase of oscillation here. Next, if we refer, we find that for the mode 2, as you can see here, that it is associated with omega here, lambda 3 and lambda 4. So when we plot them, so we find here that it is omega and delta and omega and delta. So it means that for the case of mode 2, the angular, the rotor angles of the generators here, they are in opposite phase of oscillation here. And the same information you can get it even by the using or by using state variables angular frequency or angular speed here. So for the mode 2, the generator rotor angles, they are in opposite phase. However, for the mode 1, the two generator rotor angles, they are in the same phase of oscillation here. So thus with this, with the use of right eigenvectors, we are actually able to know the phase of oscillations for the generators for the given mode here, and that says about the activity of the state variable. So how the delta state variable is associated to the mode 1 or the mode 2 here, so that we can refer it from right eigenvectors. Next, we compute the left eigenvectors, and what we find here that with the left eigenvectors, we have the row-wise modes, and then we have the column-wise as the state variables here. And with the elements in the first column, we find here that this one, right? Because here the imaginary part is 0. So we find here that for the lambda 3 and lambda 4, the amplitude is much more for the state variable, this one. However, if we refer to lambda 1 and lambda 2, we find here that the imaginary terms are 0, and we find here that the amplitude, the real part, is much more uh, for the state variable delta here. So that's it can be said that with the left eigenvector, it can be said that it is this state variable which will contribute more than this state variable to the mode 3 and 4 here, this one. So here you have lambda 3 and 4. So it is the contribution of this state variable is more than this state variable for the lambda 3 and lambda 4. Similarly, the contribution of this state variable is more than this state variable for the mode lambda 1 and lambda 2 here. So thus we are a, that means if you remember, the left eigenvector tells you the weighted contribution of a particular state to the mode. So thus for these modes lambda 3 and 4, the contribution of delta 1 3 is much more than this one here. So this information we get it from left eigenvector. Next, we move on to calculation of participation factor. So we have this matrix obtained from the previous. So we have done is Q is equal to Q transpose here. And now we are interested to determine the participation factor here. So if we refer from the participation factor along the row wise, we have the states, and along the column wise, we have the modes representation. So we have lambda 1, lambda 2, lambda 3, and lambda 4. And what you find here that this state variable, if we refer to the values for lambda 3, it is more because the imaginary terms are 0 here, and thus the amplitude of the real part. So this state variable will participate dominantly to this mode here, mode 2 here, right? That is lambda 3. Similarly, when we look at this state variable has this real part and this real part. So we find here that this state variable will participate dominantly to the mode 1, because for lambda 3 and 4 the values are lower comparatively. So and as such, the delta 1 3, it participates dominantly to the mode 2 as compared to delta 2 3. Similarly, the state variable delta 2 3, that participate dominantly to lambda 1 and 2 mode 1 with respect to delta 1 3. So that means for mode 1, we find more oscillation in this state variable compared to this one. And however, for the mode 2, we find more oscillation associated with this state variable as comparable to this state variable. So that means for the mode 1, we will have more oscillations being observed in the rotor angle of the generators 2 and 3. However, for the mode 2, we will have more oscillations being observed for the generators 1 and 3 here. So with this, I would stop here, and then I will take up some more examples for discussion on small signal stability analysis. Thank you.